Hello and welcome to this video where we're going to attempt question 3 of a June 2019 Decision 1 Maths paper by Edexcel. So, for this question we've got a network shown in figure 2 showing with direct roads linking 5 villages A, B, C, D and E. And the number on each arc represents the length in miles of a corresponding road. We're told that the roads from A to E and from C to B are one way, as indicated by the arrows. We've got a directed graph here. I'm going to answer parts A and B together. It has to complete the initial distance and route tables and perform the first 3 iterations of Floyd's algorithm. So I'm going to set up my initial distance table. And down my leading diagonal, my initial distance from A to A will of course be blank, B to B, C to C, D to D, and E to E. And these distances will remain blank because there is not going to be any route from A to A. If you're starting at A and ending at A, you don't need to do anything. So now A to B, 15. And similarly B to A, 15. A to C, 7. And C to A will be 7. A to D is 18. And D to A is 18. And finally A to E is 3. And there is no direct route from E to A, so it's going to be infinity. Next up, B to C is currently infinity. There's no route from B to C, but C to B is going to be a 5. There is also no route from B to D or B to E at all, so B to D and B to E are infinity, and similarly D to B and E to B are infinity. Next up, I've got C to D is 4, and D to C 4. C to E is 9, and E to C is 9. And finally, D to E is 3, and E to D is 3. And when setting up my initial route table, I'm going to have all the values in each column is just the title or the header of that column. So I'm going to get multiple A's, multiple B's, multiple C's, D's, and E's. Okay, I'm now going to perform Floyd's algorithm. So in an exam, you can highlight the column and row that you are for the iteration that you're on, but you need to shade it really, really lightly in pencil. So a little scribble like this isn't going to be good because that looks like you're crossing out your work. So if you're shading in pencil, it needs to be really, really similar shading across the entire row and column. On here, I'm going to use highlighter, but please don't do this on your exam. You cannot use highlighter in the body of a question. So I'm going to highlight my first row and column. So these are going to stay the same, so I can copy these down immediately. And I can also copy down my route table. And now for every other value, I'm going to see whether so for BC, I'm going to see whether the value in row B and column C is larger than or smaller to the highlighted value in the same column as the value and in the same row as a value. And infinity is larger than 15 plus 7. So I'm going to get 22. 15 plus 18 is 33, which is better than infinity. And 15 plus 3 is 18, which is better than infinity. So because I've updated these 3 values, I also need to update the route table. And my advice for updating route table is to update route table if you update the distance matrix using the letter corresponding to your iteration. But if you don't update the distance matrix, don't bother updating root table until you finish the distance matrix. So next up, 5 is smaller than 7 plus 15, so I'm going to keep this 5. 4 is smaller than 7 plus 18. And 9 is smaller than 7 plus 3. Infinity is larger than 18 plus 15, so I'm going to replace that with 33 and update the root table. 4 is smaller than 7 plus 18, so I'm going to keep that 4. And similarly, 3 is smaller than 3 plus 18, so I'm going to keep that 3. Finally, infinity, we can't really compare infinity plus 15, so we're going to keep infinity. And similarly, the other values in row E, we're not going to be bothered about because we've got an infinity. I'm going to add the dashes for the leading diagonal. And now for a root table, any letter I've not updated, I'm just going to copy from the root table previously. So I'm going to get this root table. And I'm going to do the exact same thing when performing the second iteration. I'm now going to consider the second column and the second row. So I'm going to use the distance table from before to mark this row and column onto. I'm going to carry out the exact same thing. I can copy my leading diagonal and I can copy my row B and my column B. And similarly in the root table. Now it doesn't look nearly as daunting. So I'm going to consider 7. 7 is smaller than 15 plus 22. 18 is smaller than 15 plus 33. And 3 is smaller than 15 plus 18. 7 is smaller than 15 plus 5. 4 is smaller than 5 plus 33. And 9 is smaller than 5 plus 18. 18 is smaller than 15 plus 33. 4 is smaller than 33 plus 22. And 3 is smaller than 33 plus 18. We can't really compare infinity with 15 plus infinity. And we can't compare, well, we can compare 9 and 3. They're definitely smaller than infinity plus the corresponding values above. So there's been no change to my distance table. So there's going to be no change to my root table. So I'm going to copy that down right now. And now it's time for the third iteration. So I'm now going to use C as the column and row that I'm interested in. And I'm going to perform this one last time. And now if I make an update in my distance table, the same cell in my root table will be updated with a value C. So 15, so you can copy the row and column C down. So we'll do that to begin with. And we can copy the leading diagonal as well. So we're going to do the same thing on the root table. So now we can consider the other values in the distance table. 5 plus 7 is 12, which is better than 15. So I'm going to replace 15 with 12 and update the root table to contain a C. 7 plus 4 is 11, which is better than 18. So my root table is also going to get updated. But 3 is definitely better than 7 plus 9. 7 plus 22 is 29, so 15 will remain unchanged. 22 plus 4 is 26, so I'm going to replace 33 with 26. And then 18 is smaller than 22 plus 9, so it's going to remain the same. 18 is larger than 7 plus 4, so I'm going to replace it with 11 and update my roots table. 5 plus 4 is 9, which is smaller than 33, so I'm going to replace 33 with 9 and update the root table. And last but not least for row D, 3 is smaller than 4 plus 9, so 3 stays the same. Finally, row E, 7 plus 9 is 16, which definitely improves upon infinity, so I'm going to update the root table as well. 5 plus 9 is 14, which is definitely better than infinity, so I'm going to update the root table again. Finally, 3 is smaller than 4 plus 9, so 3 is going to remain untouched. And now I can fill in the blanks on the root table with what the root table had previously. So I've now got the root table looking like this. So, mark-wise, I'm going to have got a method mark for setting up, sorry, not a method mark, I'm going to get an independent accuracy mark for setting up the distance table and one for the root table. I'm going to get a method mark for doing the first iteration on the distance table and having some values decrease. And an accuracy mark for doing everything in the first iteration correctly. You're going to get an accuracy mark for the second iteration for having nothing change. And then finally, another method and accuracy mark for performing the third iteration. So 7 marks in total for performing 3 iterations of Floyd's algorithm. And we're now told that after 5 iterations of Floyd's algorithm, we have a final distance and partially completed root table. And we can find the shortest route from E to A. So if we start at row E and read across to column A, we're going to see that it has a shortest distance of 14. We can use the root table. We're going to get that the shortest distance from E to A goes via D. So we're going to get E to A becomes E to D to A. And now got to consider how to get from E to D and D to A. So to get from E to D, we have to go via D, so we know ED is the shortest. And then D to A, we need to go via C. So we've now got EDCA. We know that ED is fine, but now we need to make sure that DC and CA are also the shortest paths to go down. So DC goes via C, so we're sure that DC is the shortest way of getting from D to C. And finally, C to A. We've got C to A, and we've got A in the root table. So we've got CA being fine as well. And it's an explain that question. So you've got 2 marks for the explanation. So saying that you start from E and read across to A and say it was D in that cell would get you your first independent accuracy mark. And then your next accuracy mark will have been from considering E to D and D to A separately. Then finally, there's one more independent accuracy mark for giving the correct route. And now we need to apply the nearest neighbour algorithm to the cycle, because we're trying to use a distance table to find the shortest cycle passing through each vertex, and we're going to start at D. So starting at D, we really want to go to E next. So we're going to get D to E. Starting at E, we then have A and D are the nearest neighbours to E. We can't go to D because we can't return to D yet. So we're going to go to A. The nearest neighbour to A is C. And apologies, I've been reading this kind of backwards actually. So I've been reading the to vertex first and then going to the from vertex, which is a tiny bit awkward actually. So let's start this again. So to get from D we need to look at the row D. So the nearest neighbour to D is E. So we're going to go D to E. Now we're going to look at row E next. And the nearest neighbour to E is currently D, but we can't return to D until the end. So the next nearest neighbour is C. Now we're at C, we can't go to D or E next, so we're forced to go to B next. And now we're at B. The only neighbour we can visit is A, because A is the only neighbour that's not been visited. Then finally, we've got to return to D. And we need to state the length of this cycle. So D to E has distance 3, E to C had distance 7, C to B had distance 5, B to A had distance 15, and finally A to D has distance 6. So if we add all of these up, we're going to get 36 miles. Interpret the cycle in terms of the actual villages visited. So to have gone from D to E to begin with, let's look at the graph that we're given. D to E, distance 3, is a direct route. So we're going to get D to E, then E to C with a distance of 7. Well, the only way to go from E to C with a distance of 7 is to go via D. So E to C is going to be E to D to C. C to B with a distance of 5. We can see we can go from C to B. So we're going to write C to B down. We've now got to go from B to A with a distance of 15, which we can do, B to A. Then finally we've got to get from A back to D with a distance of 6, which you see we can do going via E, so A to E to D. So actually to get from D to E to C to B to A to D, we have to go D to E, but then we have to go via D to C, then on to B and on to A, and to get from A to D we have to go via E. And finally, we need to prove that the cycle is not optimal. So we need to prove that this cycle of 36 miles isn't optimal. And how are we going to do that? Well, to do this, we just need to look at our graph and try finding a cycle that's shorter than 36 miles. And looking at this, I'm spotting a cycle now, starting at A, I can go to E, to D, to C, to B, and back to A. And this cycle has a length of 3, plus 3, which is 6, plus 4, which is 10, plus 5, which is 15, plus 15, which is 30. So cycle A, E, D, C, B, A has a distance of 30 miles, which is less than 36 miles. So original route was not optimal. So looking at the marks of part D, and we've got 4 independent accuracy marks. We've got an independent accuracy mark for this, for 36 miles, for this route, and for this analysis. So thanks for watching, and until next time, goodbye.